Welcome to this explainer. Today, we're going to absolutely hack the Simplex method, giving you the exact mental frameworks you need to retain this pretty complex linear programming algorithm for your LECPA MAS exams. Look, if you're a BS accountancy student right now staring down management advisory services, you already know that cramming just doesn't work. We need real 3-year retention here. We have to optimize exactly how your brain processes this information so that when you finally sit for the boards, this logic is completely second nature. So let's dive right in.
We've got a strict, strategic 5-step agenda to chunk this data effectively. We'll hit the Simplex core objective, converting to standard form, setting up the Tableau, iteration rules and pivoting, and finally, those crucial LECPA retention hacks.
All right, starting with Section 1, the Simplex core objective. What exactly are we trying to do here?
Now, graphical methods are great and all, but honestly, they're super limited. They work perfectly when you only have 2 variables to plot on an X and Y axis. But the real corporate world, the world you're actually going to be auditing and advising, it's messy. The Simplex method is your algebraic heavy lifter when a company has multiple products, multiple departments, and a whole bunch of complex constraints. It is literally the mathematical engine for serious resource allocation.
And listen, the secret to retaining this isn't memorizing some massive, terrifying formula. You have to think of it not as a static math equation, but as a dynamic loop. It's an iterative algorithm, meaning you systematically move from one feasible solution to a better one, over and over, until your profit is completely maximized. It's really just a cycle.
Moving into Section 2, converting to standard form, we gotta prep our constraints. In accounting, everything has to balance, right? You know this. So ask yourself, how on earth do we turn a less than or equal to or a greater than or equal to constraint into an exact equal sign? The Simplex algorithm just cannot process inequalities. It demands absolute perfection.
Well, this brings us to a brilliant anchor metaphor. We use what are called slack and surplus variables. If you have a less than or equal constraint, you add a slack variable. Your mental schema hook here? Slack represents unused resources, kind of like unspent budget or idle machine hours. On the flip side, if you're dealing with a greater than or equal constraint, you subtract a surplus variable to strip away the excess. Boom, it balances the equation perfectly.
Check out how this maps out visually. Our original inequalities on the left, pretty messy, but by introducing those slack variables, x3, x4, and x5, we physically force those less than symbols to become equal signs. We now have the augmented standard form, and our data is officially primed and ready to be loaded right into the matrix.
Which perfectly cues up Section 3, setting up the Tableau. Let's load up that operational matrix.
Every great algorithm needs a starting line, right? For the Simplex method, initialization always begins at the origin. The logic here is incredibly simple, and you should definitely lock this into your mass notes. Before we produce a single thing, our initial basic feasible solution assumes zero production, meaning all of our limited resources are currently just sitting there idle in our slack variables. Zero profit, total slack.
And here is what that looks like in your initial Tableau. Notice how row 0, that top row, contains our objective function, which tracks our profit, Z. Right now, on the far right side, profit is exactly 0. Meanwhile, the basic variables column is strictly tracking our slack resources, x3, x4, and x5. Like we said, we haven't built any actual products yet.
All right, Section 4, iteration rules and pivoting. Let's get into the optimization hacks. Remember earlier when I said this was a dynamic loop? Well, we're going to chunk this iterative loop into 4 precise steps that you'll repeat until you achieve the absolute perfect product mix. Optimality, entering, leaving, pivoting. Let's break them down real quick.
First up, you need a quick trigger for your exams to know if you actually need to keep doing math or if you're already finished. The rule is super simple. Look at the top row, row 0. If every single coefficient in that row is 0 or positive, you're done. The current solution is optimal. But if there's even one negative number sitting there, it's a signal. It means your profit can still grow, and you have to iterate.
So if we know we can make more profit, the big question is, which product do we make first? Your entering variable is the column with the most negative coefficient in that 0. This right here is your strategic hack. Choosing the most negative coefficient guarantees you're picking the product that gives the absolute fastest rate of improvement to your bottom line. It's pure ROI, guys.
Okay, so we know what product is entering production, but resources are limited, obviously. As we produce more of the entering variable, we use up our slack. To avoid violating our non-negativity constraints, because, you can't have negative raw materials, we have to find out which resource acts as our bottleneck. Basically, which resource runs out first.
To figure that out requires a very specific test, the minimum ratio test. You take the values on the far right side of the tableau and you divide them by the strictly positive coefficients in your entering pivot column. Whichever row gives you the smallest positive ratio identifies your leaving basic variable. This is the exact constraint that completely stops your production expansion in its tracks. It is your ultimate bottleneck. Once you've successfully identified your entering column and your leaving row, their intersection gives you your pivot number. Now you perform elementary algebraic row operations, which is essentially just Gauss-Jordan elimination. Your goal here is to force your entering variable to have a coefficient of exactly 1 in that specific row, and 0 in every single other row above and below it. After doing the algebra, your brand new Tableau emerges. And just look at the right side. Our profit Z has jumped from 0 all the way up to 30, and X2 has officially entered our basic variables column, replacing that bottleneck slack variable. But check out the Z row again. There is still a -3 sitting there for X1. That means we aren't done yet. You simply loop those 4 steps all over again until every negative coefficient in the top row is completely eliminated.
Let's wrap this up with Section 5, LECPA Retention Study Hacks. Time to consolidate this for active recall.
Take a mental screenshot of this exact summary right now. Burn this into your brain. Standard form means slack is unused, surplus is excess. When you iterate, the max negative enters because it's your highest ROI, and the minimum positive leaves because it's your strict bottleneck. You perform Gauss-Jordan, and you absolutely do not stop until row 0 is entirely positive. That is when you've hit optimal profit.
As you map these strategic algorithms to your MAS accounting knowledge, I really want you to think beyond the math. Ask yourself, how can you apply this exact same optimization logic to maximize your own LECPA prep over the next 3 years? Find your bottlenecks, eliminate your slack, and absolutely maximize your results. Keep optimizing, and I'll catch you on the next explainer.